as Master Black Belts from American Society for Quality, and we're here to talk about the second phase of the DOE, and I hope you all had an opportunity to see the very first one. The first one was on a process that's commonly called an attribute output from the process, and the process was, in that video, was an analysis that was either pass, fail, yes, no, or something along those lines. This one's going to be a little bit different. It's going to be along the lines of variable data. And variable data, and this particular example, will be one that has yield as one of the outcomes from it. The yield will vary anywhere from 75% up to 95%. So it has infinite number of possibilities between those readings. So we're going to call this variable data. The mathematics and the analysis behind it are a little bit trickier and a little bit more difficult to do, but nonetheless, this is a very, very powerful tool. Once again, just like the last one, this will be a 3-factor, 2-level, 8-run design of experiment, and it will be from a very fictitious sanding operation with fictitious data off of it, but one that I've probably used 10 to 12 times in various cabinet making and sanding facilities throughout the United States. So I hope you watch this one in conjunction with the one that you just saw. Hopefully these two will give you a very good base of design of experiments. So let's jump in, let's go to the next phase and start the analysis phase and understanding of how you do the computation behind it. Okay, let's get into the analysis and the design of the DOE. For those of you that have seen the original DOE that we did on the last one with the attribute data, what we have here is a base level 8-run DOE. And we're going to take run number 1, 2, 3, 4, 5, 6, 7, and 8. And we're going to take the force level and the speed and the grit. We're going to put them on each one of the columns. And we're going to take the force and we're going to go minus plus, minus plus, minus plus, on down for our 8 runs. For the speed, we're going to go minus minus, plus plus, minus minus, plus plus. And for our grit, we're going to go 4 minuses followed by 4 pluses. When we do all this, it's called full factorial. And this essentially covers the respective combinations, or all combinations, between the force, the speed, and the gravity. Now, as you went and run this, you wouldn't run it in the order that we have here. And that's what I've included over here, where we actually did run it in, and this was the actual run order, as it was put into a random number generator, and came out, and then we ran it to number 1, which was actually designed run number 3. We ran that one first, and then ran the second run as number 6, and so forth. Idea behind that is if I ran it in this particular order, gravity is now going to be the first 4 runs, and potentially in the last 4 runs are going to be turned to positive, and if I had the first 4 runs that were run under an environmental change in the process, we might be what's called confusing or confounding the environmental factor with the gravity factor coming off of it. So we don't want to do that. So what we've done is we've done an actual random order generator and put it through in many software programs, and we've generated it in a different order than what we've got for design order. But let's go through as if this was a design order now. We ran the first run, and we ran it with the particular force at the negative level, which I believe was at the 31 level. The speed was at the 500 level, and the gravity was at the grid of 500. And then we came up with a yield coming off there of 83%. We did the same kind of similar process for run number 2, came up with a yield of 86, and so on throughout the process. Now, before we get into the analysis of the rest of the numbers that we have up here, what I'd like to do, and I strongly suggest everyone to do, is to develop the cube plot. And first off, stop right here and visually see what you've got. So let's take the draw cube plot. On the left-hand side, we have our cube plot consisting of our three variables, the pressure, the speed, and the gravity. And the blue line represents each one of the runs. Run number 1 was with all three settings at the negative level. Run number 8 was all three at the positive level, and the respective runs in between there at the respective levels in the cube. Notice that we have all corners of the cube plot covered. There is times when we will actually put a what's called a center point into the process, and we'll cover that in a later video. But for now, let's just determine what the analysis will look like once we get it all set up. So let's go to the other side over here, which we have a similar similar cube plot. Cube plot consists of the pressure, the speed, and the gravity, minus the plus level, minus the plus. And on this particular side, we've included the actual yield coming out of the process, anywhere from a low of 83 to a couple other 90s up here and so forth. So analysis of this house, in comparison to the last video where we did it with attribute data, analysis is a little bit more difficult. And visually, it's a little bit harder to see what the main effect or what the interaction effects might be between them. So that's what we're going to go to next. So let's determine an analytical method of determining what the factors are. So we'll get this board switched over. So one more time, we've got our design run, our actual run, our force, our speed, our gravity, and our yield coming out. So what we're going to do next is we're going to come up with called a table of contrast, and it's we'll go through the computation off of it, and when we do that, I'll show you how to come up with these numbers down here. Now these numbers down below here are going to represent something in terms of the main effects and in terms of what are called the interactions coming off of it. But let's start now with the development of all these numbers inside the table of contrast. What we have over here is coded F times S, or the force, speed, interaction between those two variables. And we got a plus in our first column and a minus in our second column continuing on. Well, how do we come up with that? Well, let's take these two columns and the two signs in here. Remember, the minus represented the low level and the plus represented the high level of the design. And let's take that and convert them, and let's put an imaginary 1 in front of it. So if you see a plus, it's a plus 1. If you see a minus, it's a minus 1. And all we're going to do is we're going to take the two of these variables, minus 1 times the minus 1, multiply them together. Minus 1 times minus 1 comes up with plus 1, and we'll record it as a plus over here. Similarly, a plus and a minus comes up with a minus, minus and a plus, so minus, 2 pluses is a plus, 2 minuses is a plus and a minus is a minus 1 times a plus 1 is a minus 1, and two pluses is equal to plus. We can continue and do that for not only the force by the speed, but we can do the force by the grit interaction. We can also do that for the speed by the grit interaction. And we can also do it at the three-way interaction, the force by the speed by the gravity. Now let's walk through that one to make sure we understand the computation on that one. If I take the minus on that one times the minus 1 on that one, it comes out to be plus 1, times the grit, which is minus 1, plus 1 times the minus 1 comes out to be a minus. So I'm taking all three of these numbers and multiplying together to come up with these numbers. That's part number 1. So now we've got this table created over here. We also have these as plus minus through our analysis. So what we're going to do next is we're going to come up with these numbers down at the bottom. And these numbers and the relative magnitude of these numbers have a distinctive meaning in the analysis portion of design experiments. So what we're going to do now to come up with the force by speed interaction is that we are going to take, everywhere we have a plus, we'll take all four of those pluses, the 83, the 93, the 84, and the 93. We will average them out. We will average them up and divide by 4. And then we will subtract off of there the minuses coming off of it, the 86, the 83, the 84, and the 87. So we'll take the first, we'll take all the pluses, the average of all the pluses, minus the average of all the negatives. And we'll come up with the difference between the two. And the difference between those two comes up to be 4.25. We can also do that for the force by gravity, and it comes out to 0.75. The speed by gravity, which comes out to 0.25, and the same exact procedure for the three-way interaction for the force by the speed by the gravity for 0.75. We can also do it on our main effects. The main effects being in a similar way. For our force, we can take all the negatives of the 83, the 83, the 84, and the 83 and average those up. And we can subtract those off of the pluses, which is the 86, the 93, the 84, the 87, and the 93. And that one is basically comes out to 7.25. We can do the same thing for the speed. It comes out to 3.75. The gravity comes out to 1.25. All right, so we've gone through the mathematics of the development of this board. And we've come up to a series of analysis out there. We've come up with a main effect. Now let's interpret what that force means. It means when we went from that high level of the force down to the low level of the force, we went from a 37 down to a 31, and actually reduced the yield by 7.25 units. Quite a big chunk of change when you look at the overall process and the overall yield coming out of this unit. But also notice that changing the grit paper from a 300 to 500 level only changed the yield by 1.25 percentage points. And relative to the other numbers that we have down here, that's basically noise in the process. So if you look at look at all the roles and look at the three main effects with the three two-way interactions and the one four-way interaction, what really stands out? Well, you can do some analysis on it and you could compute out what really stands out from a statistical standpoint. But there's two, and there's actually a third one. There's the force. There's the interaction between the force and the speed, and there's the speed. Now what we're going to do in the next step is we're going to convert these numbers and we're going to graph out those three graphs and determine graphically what's the process telling us. This interaction effect has a major dominant effect that needs to be analyzed in front of before you get to the force and before you get into the speed of the process as far as the main effect goes. This is kind of the hidden gem that's going to show up when we do it, when we look at it another way. Okay, so let's get into the process. The process, as described up here, is a sanding operation. We have a sanding drum and a pine board that is passing underneath it. We have a certain rotational speed. We have a certain force that's coming down, and we have a certain grit of the paper that we're utilizing off the process. The specifications on it are determined for the process coming out. We're going to measure what's called yield coming out of it in board feet as a percentage of the maximum that they could possibly get out of the process. And so this is kind of the overall objective of what we're trying to do. There is actually a fourth variable out here, and it is the linear speed of the board as it goes through there. With discussion with the operators, this was almost nearly impossible to change. So what we're going to do is we're going to limit it to those three variables and only those three variables. So just like the last variable, or just like the last video, how would we do this? Well, we'd get our team together consisting of a subject matter expert, the champion of the process, and potentially the Six Sigma black belt, and probably 1 to 2 of the operators that have been operating this unit for a while now. And the objective of all this thing is to maximize the amount of yield that's coming out of the process. So we have established what our three variables are: the force, the rotational speed, and the grit. And when we get everyone together, what we do is we go through and we determine, okay, as we did in the last video, take the force. What's the maximum force that you could potentially run this thing at? And what's the minimum that you can run it at? And we're going to do that without destroying the equipment, but we're going to move it out so we can get some movement out of that process to determine what the force factor is when we run the process. So we're going to take it, and after doing all this process, we were running it at an average of 31 kilonewtons, and now we're going to take it down to 27, and we're going to take it up to 35 for our two experimental levels, 27 to 35. Same thing with the rotational speed. And we're going to call these in the rotational speed, we're going to call it an S, and we're going to do it in RPMs, and the RPMs will be anywhere, we'll take it normally runs at 650, and consensus by the group, we don't want to lower it less than 500, and we will take it up to a maximum speed of 750, which is the maximum speed of the equipment. And then the final variable in the whole process is the grit, is the sandpaper grit. And we're going to take it from a grit of 300 up to 500, and normally run around 400. They have opportunity to almost use an unlimited number of grit sequences throughout between 200 and 700 off of it. They strongly advise against using 200 off of it because the effectiveness will be very low, and it's the same with getting anything above 500 as well. So those are the three measurements, and then what we're going to do is we'll put them into a standard, like we did on the last one, 8-run, 2-level, 3-factor DOE, and then we'll run them, and we'll measure the output in linear or in percent of the linear feet, the maximum value off of it, and we'll call that yield. And we'll go through the analysis process with variable data. Okay, let's continue on with the analysis. Right? We have our Q plot now. Let's go back to our Q plot analysis, and what we're going to do now is we're going to convert these into what are called interaction plots. Interaction plots are commonly done in computers and Minitab and jump software and so forth, but if you understand how to do it by hand, the interpretation of them will be a whole lot easier. But one more time, we have our force, our speed, our grit of our paper, and our respective yields associated with each corner of the cube plot. So let's look specifically at the two-way interactions, and then I want to talk to one of the main effects. And all we're going to do is we're going to do two of those two-way interactions, the force by the speed one, and the speed by the grit one. So what we have here is a graphical representation of what is commonly called two-way interaction. And so the development of these two-way plots, if you look at the force, we go from a minus to a plus along the x-axis. Along the y-axis, we go from an 80 to an 85 to a 90. That is our output of our process. The solid line represents the speed at the plus levels, and the dotted line represents the speed at the minus levels. Notice that when you add a force of minus, that the speed really doesn't make much of a difference in the process at all. Basically, the yield coming out of it is right around 85. But notice when we increase the force up to a plus, up to the high level, what happens to our yield of our output? Well, at the again, if the speed is at the slow speed, it really doesn't make much of a difference. But if we put the two of them together, the fast speed in conjunction with the high force, the yield jumps all the way up to approximately a 93%. This graphical representation is called a two-way interaction. It's one of the most critical finds you're going to find in design of experiments. The only way you're going to find this out is through design of experiments. Doing experiments one factor at a time would not yield this type of an output. I want to compare that to the one below it, which if you remember from from 5 minutes ago here, that the speed by the grit was actually benign, or it had there was the zero of the output from it was about a 0.25. If I plot out the solid line, which is the grit at the high level, and the speed at the low level, and I put a point there that the solid line represents all the grit at the high level. The dotted line represents the grit at the low level. Notice in terms of the speed, when we go from a minus to a plus, that the lines are parallel to one another, and that the separation at the low speed in comparison to the high speed is identical at the two settings for the grit. This is a classic interaction that is called benign. It's actually not there. This is one that is actually there. The busiest and easiest way to tell the difference between the two, other than through the cube plots, which I'll show in a minute here, is the slope of the lines, or excuse me, the parallelism of the lines. If you graph them out right, the parallelism of the lines will dictate to you or tell you where the interactions are at. In this particular case, there was this very distinct two-way interaction going on between the force and between the speed. Now, those are the two-way interactions. Three-way interaction plottings gets a little bit more difficult. It gets we'll cover that in later videos, how to plot those out and interpret those. But the main effects plot, or each factor taken by itself, is also the other critical factor on it. And notice, remember from the prior 5 minutes ago, we have one of the main effects being the force, and that showed an approximate 6-point increase when we went from minus to positive. That one is probably the most easiest one to interpret. Why do I say that? Well, I'm going to take all the negative readings and average them out and plot them, and I'm going to take all the positive readings and average them up and plot them, and I'm going to get an approximate 6-point increase in my yield when I go from the force at the low level to the force of the high level. But notice if I had just looked at the main effects and not at the interaction effects, what I would be missing. I might be looking at this and interpret all I have to do is move the force up to the positive level, and that will give me a main effects of right around 90. A nice increase from where we were at, probably around an 85 to a 90, or from 85% up to 90%. That's good, but it's probably not the best you can get. Why do I say that? Well, because if you look at the interaction between the two, if not only you raise the force, but if you raise the speed at the same time, then you're going to get a yield someplace around 94, 95%. Another 3% increase off the process, which from a 90 to 94 might be enough to make the process profitable versus not profitable. Now, all of this is a graphical representation of it. You can also see it when you plot it out on the cube plot. If you look at the cube plot and you have it graphed out correctly, well, what are we doing? Well, we were taking the force, the main effect one, and we were taking the 83, the 83, and the 84, and the 85 and average them up to come up with that point. And then we were taking the 93, 96, 87, and 86 and plotting them out to come up with the next point off of it, which gives you the effect of going from this plane to the plus plane. So where is the interaction effect coming from? Where are we coming up with that approximate 95% yield off of it when the two are acting together? Well, the two acting together was when the speed was positive and the force was positive. And where are those points at? Actually, they're right there. It's represented by the 93 and by the 96, or the upper right-hand corner of the box. Classic two-way interaction. That if you did it by just looking at the main effects, you would potentially run it at a different level and lose the effect you would have off of the increase in yield. That's the analysis of a variable type of DOE. Very simple once you break it down, and but a little bit more complicated than doing it with a attribute type of DOE. The next phase we're going to get into will be into DOEs that get a little bit more complicated, get into half factorials and things like that. But this DOE behind me is probably one of the classic ones, and one that will yield you probably the most benefit in most projects. So I hope you use it, and hope to see you implementing DOEs on a constant basis.